Right about 1800, within about 5 years of 1800, a guy named Carl Friedrich Gauss comes up with the fundamental theorem of algebra. And what he says is that if you have a polynomial, any degree, n greater than 0, meaning that it's at least a first degree polynomial, there is a variable involved, then it has at least 1 0. So Gauss in about 1800 proves that the fundamental theorem of algebra is that if I have a polynomial, it has a 0. It must. And it led to a lot of what we're doing with factoring and graphing and finding zeros of quadratics and all this kind of wonderful stuff. Gauss's theorem is really what sets the basis of this. And shortly after his death, about 20 years, whatever, it comes out that with the linear factorization theorem comes out, and it says that if it's degree n, it has precisely n linear factors. So if it's fourth degree, it has 4 factors. If it's fifth degree, it has exactly 5 factors, not more, not less. And it was an extension on what Gauss first found in 1800-ish. And if we have problems that look like this, find all zeros of 2x cubed plus 8x squared. How do we go about factoring this? What do we do first? Take out an x. Is there anything else I can take out? A 2. So I'm going to factor out the common factors. Now, can I factor x squared plus 4? Are they perfect squares? Yes. But is it the difference of perfect squares? It's not. So we can't factor this guy. But what we can do is set each part equal to 0. And get x equals plus or minus 2i. So my zeros of this equation are 0, 2i, and negative 2i. It's a third degree polynomial. I have 3 solutions. Life is good. All right. Now, 2i and negative 2i, we had a term for those last week. What do we call those? Well, yes, they're both imaginary. Well, how are they related? Maybe if I write them like that. How are they related? Starts with a C. Yeah, they're conjugates. So they're conjugates of each other. So two of the zeros we found are conjugates of each other. And it actually leads us to a theorem that says that complex zeros are always conjugate pairs. So that means that if one of my zeros is imaginary, its conjugate has to be a zero as well. So if a plus bi is a zero, a minus bi must be a zero. And the reason is that a number times its conjugate, an imaginary times its conjugate, is real. And the only way to factor a real out of a real, or to factor those imaginaries out, is to make them real. I have seen multiple tests that say if 2 plus I is a factor of blah, 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 what is another guaranteed factor? Well, if 2 plus I is a factor, then 2 minus I has got to be a factor too. So if negative 4 plus I and negative 4 minus I are two of my zeros, negative 4 plus I, negative 4 minus I, distribute x plus 4 minus I, x plus 4 plus I. Do the exact same thing, multiply it out, x plus 4x plus xi plus 4x plus 16 plus 4i minus xi minus 4i minus I squared. It's the same way. I just multiply the two polynomials together. Xi, negative xi, 4i, negative 4i. Leaves me with x squared plus 8x. I got 16 minus a minus is a plus. I end up with 17. And then I do my polynomial long division. And hopefully this will be a little nicer. Wait a minute. What? I just can't multiply. My fault. I just can't multiply. Sorry. I'd multiplied by 2 for some reason. X squared 2. Yes.
negative 8x squared minus 64x minus 136 minus 8. That's minus 8x squared minus 64x and minus 136. So yes.
So it does divide out evenly, as it should, because they're factors. If they're factors, it must divide out evenly. Whee! I just didn't draw the last thing. So, I mean, okay, now, so all I've done is I've factored out the two imaginary parts. I still have to find my other two zeros, but now I've got it reduced down to x squared minus 2x minus 8, which simplifies factors very easily into x minus 4, x plus 2. And so what are my other two factors? 4 and negative 2. So all four of my zeros, negative 4 plus I, negative 4 minus I, 4, and negative 2. It's fourth degree, 4 zeros. That's a beaut. Yeah, these require a little bit of paper. So that's one type of problem that you're going to see. There's 4 types total we're going to talk about because I'm like, these will trip them up. Second type. I know the rest of the problems are fine. Looks very similar to the last one, doesn't it?
No.
What didn't they give me this time?
136.
They didn't give me any of the zeros. How do I start? How can I start factoring? There's no common factors. They don't all have them.
Undefined.
No, definitely not.
Yes.
What's that? The rule of zeros thing? Does that apply to this or not?
It does.
Not a quick
You can do that thing?
Okay. Are you talking about Descartes' law of signs?
That's it. Yeah.
Okay, yeah, I can definitely do Descartes' law of signs because Descartes' law of signs, I count the number of sign changes. 1, 2, 3, 4. And by Descartes' law of signs, that means that I have 4 positive roots. Or remember that it could be any factor of 2, so it could be 2 or 0. If I plug in negative x, change all of the odd index ones, then everything becomes positive and I have no sign changes. So I can't have any negative roots. I could have 4 positive, 0 negative. So Descartes' law of signs tells me all 4 of my roots are going to be positive. Cool. How do I find my possible roots? What was the other thing that we learned at the same time we learned Descartes' rule of signs? The P over Q, the rational root theorem. Remember, the rational root theorem says if I take all of my factors of my constant. So that's 1, 2, 4, 8, 16 over all of my factors of my leading coefficient. Fortunately, it's just 1 in this case. That I end up with a list of possible zeros, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16. Those are my possible zeros. Now, what did Descartes' law of signs tell me? That none of them are going to be negative. So I'm not going to even fuss with -1, -2, -4, -8, -16, because Descartes' law of signs tells me none of those can work. Cool. So I'm going to set up my synthetic division. And about now is when I like to switch to pencil so I can erase, because I'm probably going to pick some wrong ones. Like, okay, let's try 1. So 1, 1, -3, -3, 5, 5, -11, -11. That didn't work, right? Okay, so I know 1 isn't one of my options. So that's why I do it in pencil. So I don't have to write the whole thing down again. Now I'll try 2. 1, 2, -2, -4, 4, 8, -8, -16. Look at that. I found one of my zeros. So 2 was one of my zeros. And remember, when I do my next synthetic division, I don't have to start at the beginning again. I can start where I've already factored one of them out. What number would you like to try next? Sure. 1, 4, 2, 8, 12, 48. No, that doesn't work. So you're saying 4 won't work, 8 won't work, and 16 won't work. I agree. So then what? Can't try any of the negatives. We know Descartes' law of signs, they won't work. Multiplicity. So what can I try again? I could try 2 again. It could have a multiplicity of 2. 1, 2, 0, 0, 4, 8, 0. Look at that. 2 worked again. Now, I get to this point where I end up with a trinomial. Stop doing synthetic division. Just write it down. X squared plus 4 is when I write this down, and just factor this out or set it equal to 0. Well, I can't factor this. Subtract 4 from both sides. Take the square root, and I end up with plus or minus 2i. So my roots then are 2i, -2i, and 2. And you could put that this does have a multiplicity of 2. Now, here's the crazy thing. Do you realize how many new concepts are in this one problem? A lot. There is a ton of new stuff that we've built up and broken down into pieces to get to be able to be at this spot. And as we move through this class, you're going to find out why are zeros so dang important. And as you get into calculus, you find, oh my gosh, they're crucial. All right, third type. I mention this because most of you have forgotten this. Could I do this one the exact same way? P's over Q's, Descartes' law of signs, yada, yada, yada. Yes. Yes, you could. Have fun. Because 50, you got 1, 2, 5, 10, 25, and 50, and then you have 1 and 3. So, you know, you're going to have 20 possible zeros. Might take you a minute. Why I put this one here is because what you forget is that if I have 4 terms, I can factor another way by grouping. Group the first 2, group the last 2. Take out their common factors. And then factor out the 3x minus 2. So this one's easy enough. Add 2, divide by 3. This one, though, it doesn't factor. So I set it equal to 0. So my 3 zeros are 2/3, 5i, negative 5i. It's a lot easier if you remember that factor by grouping thing. So if it's third degree with 4 terms, remember factor by grouping is often an option, typically an option. That's why I put that one there. Could you do the P over Q's? Yeah, you're going to have to find 2/3 though. I'm pretty sure you're going to go through 1, 2, 5, 10, 15, 25, 50, all their negatives before you even start thinking about the fractions. So yeah, have a good time. You're going to be, 24 on your 25th one. Maybe you'll get lucky and choose 2/3. So, but I would just remember factor by grouping. The last one. The last one they love, generally speaking, on tests, because this is one of the problems that kids that know it can do it in 30 seconds. Kids that don't know it, it demonstrates that they don't know what they're doing. It's a great problem. What kind of factoring is this? What do they call this? Difference of, difference of 2 perfect squares. So because x to the 4th is x squared squared, 81 is 9 squared. So I can factor this into x squared plus 9, x squared minus 9. And then if I look here at x squared minus 9, what do I have again? I have the difference of perfect squares again. X plus 3, x minus 3. So if you recognize the difference of 2 perfect squares as a factoring method, this factors in 10 seconds, literally. You don't even have to think, oh, done. Okay, so negative 3, 3, set that equal to 0. Subtract 9, take the square root, I get plus or minus 3i. And so 3, -3, 3i, -3i. If I'm doing this on a test, this problem literally is 30 seconds. Because you see, if you see the pattern. That's it. That's all she wrote. Assignments on WebAssign. Remember, tomorrow is ACT